another meeting that we will cover new material before your midterm 2. Chances are we'll briefly talk about reactions of ideal gases and also link equilibrium constant with some of the state functions we discussed. So that's 6.1, 6.1 to 6.3. And then whatever we finish talking about on Wednesday's class will be our cutoff line for your midterm 2. And we'll have more information posted regarding your midterm 2 after our Wednesday's lecture. So right now I don't know how far I can go, so I can't tell you what's the coverage. And then on Friday, we'll have our buffer lecture. So it's gonna be a quick review on topics we went over and maybe do some practice problem together. All right, any questions on that regard? No? Okay, so let's get started. At the end of our last lecture, we quickly introduced the idea of conventional entropy. So unlike enthalpy or like internal energy, it is easy to define those properties for a specific state. Now, when we're talking about entropy, if you remember the definition of our entropy from the second law of thermodynamics, we're talking about the differential of S equals to the differential of a reversible heat transfer over temperature. Later on, we build the link between entropy and probability. So the absolute entropy is K ln P plus some constant, right? So remember the nature of entropy while we're talking about it, it's a probability. We're talking about the probability of a thermodynamic event taking place. Now, that means when we're talking about chemical reactions, it's hard to talk about the absolute entropy of a specific state, right? Unless we're talking about very ideal situation, you can't measure the probability of a specific thermodynamic state. So with that in hand, typically in chemistry, we're talking about relative entropy. So it is nice for we to introduce the concept of conventional entropy, which is very useful for chemistry applications. So when we're talking about the definition of conventional entropy, we must have a reference point. So the reference point we pick here is we're saying the molar entropy of all the elements in its stable condensed form. So that means we're likely talking about a solid. It's a condensed form, a solid or a liquid. It can't be a gas. And we're talking about a stable condensed form. So it's like a perfect crystal of any of your given elements. Right? It's also easy to imagine. That's our reference point. We're just setting the molar entropy for each of element in its stable condensed form at, well, P equals to 1 bar to be 0. And from there, we then can use our third law of thermodynamics to make this setup more general. All right, so that's our starting point. Then what we have is our third law of thermodynamics. We went over this briefly. So the third law of thermodynamics is more or less a experimental observation and then followed by like theoretical connection to the actual principle. So the experimental observation people made is that the slope of delta G naught versus temperature, so that slope of a reaction will approach 0 when temperature is approaching 0. This is also quite straightforward to understand if you think about delta G naught of a reaction that's related to your reaction equilibrium constant, which we will cover in our future lectures. But right now, you can imagine a link between delta G naught and your equilibrium constant. And naturally, when our temperature approaches 0, all of our reaction got shut off, right? So it's natural to imagine what exactly is that observation. And based on that, we use our Gibbs equation, so negative S equals to partial derivative of G over T at constant pressure. So if my partial derivative of G over T at constant pressure goes to 0, your delta S goes to 0. Or when we write it in the more general form, we have our third law of thermodynamics. So it's saying for any isothermal processes that involves only substance in internal equilibrium, the entropy change goes to 0 when temperature goes to 0. So that's our term here. When temperature goes to 0, your delta S equals to 0. So that's a quick review on what we covered in our last lecture. So with these two pieces of information, we now try to generalize our understanding on what is the relative entropy, what is the definition of our conventional entropy. Let me just write those two things on the board so we can keep referring back to it. So the first thing we're saying is the molar entropy at 0K, or when we say like when temperature is approaching 0K, my standard molar entropy equals to 0 for elements in condensed form. And then we have our third law of thermodynamics. So when temperature approaches 0K, my delta S equals to 0. And we're going to use these two pieces of information to generalize our conclusion from elements in condensed form into more generally applicable. So let's look at that derivation together. So imagine we have a random reaction, which is a formation reaction from its elemental form. So in this case, you can imagine this to be any formation reaction from its elemental form. I'm just using water from H2 and O2 as an example. All right, so we're talking about things in their condensed form. So we're talking about solid H2 and solid O2 going to formation of solid H2O. All right. So a few things we know. For example, at 1 bar, for this reaction, for this formation reaction, you can write that delta S equals to the standard molar entropy of your product minus the standard molar entropy of your reactant with the coefficient in front of it, right? So these are your stoichiometric coefficient, negative for reactant, positive for product. And then let's use these two equations here, these two relationships here. First one we have is this relations, right? We're talking about the standard molar entropy of these elements in their stable condensed form equals to 0 when your temperature is approaching 0K. So in this case, my H2 and O2 solid are in their stable condensed form. So using the relationship here, we have, well, when temperature approaches 0, your standard molar entropy of H2 equals to 0, and your standard molar entropy of O2 equals to 0. All right, so these two terms equals to 0. Right. And then we're going to use our third law of thermodynamics. So we have the delta S for any isothermal processes when your temperature is approaching 0. Your delta S for the process equals to 0. So in this case, what do we have? Is this delta S equals to 0. And naturally, using these two relationships together, we have the standard molar entropy of water when the temperature is approaching 0. This also equals to 0. All right. Or the take-home message here is you can do this kind of transformation for any complex or any chemical you can imagine, right? As long as you can write out an equation of a formation reaction, you can use the same logic to derive that the standard molar entropy for any molecule will equal to 0 when temperature approaches 0K. Or we further generalize this relationship into like any substance, any chemicals will equal to have the standard entropy equals to 0 when temperature approaches 0. So let me just write down what we said. So when we write something like this, we're saying that the standard molar entropy at 0K, it's the same to write when the temperature approaches 0. the standard molar entropy equals to 0 for any elements or a compound. All right. We can further generalize it one more step by removing the superscription here. So that superscription denotes we must have the pressure equals to 1 bar. But if we're considering an isothermal pressure change, what do we have in that case? So again, for any processes where your temperature is approaching 0, the delta S will equal to 0. So we're using our third law of thermodynamics again. Only like this time, we're not talking about delta S for a reaction. We're talking about delta S for a isothermal pressure change. So this term also equals to 0 for the pressure change. Or the other way to put it is we can further simplify it so that the molar entropy for any substances when the temperature approaches 0 is equal to 0. All right, and not only molar entropy. I mean, if molar entropy is 0, then your entropy also equals to 0 at 0K. Or this is also another version of the third law of thermodynamics, is to say the conventional entropy of any element or compound in internal equilibrium, means it's not reacting with each other, is 0 when temperature approaches 0K. All right. So this one is just go over the third law of thermodynamics and give a definition to our conventional entropy. We're talking about a reference point from the 0K to whatever actual state we're talking about. Now, with that in hand, we're ready to use or to derive our conventional entropy and actually see how do we calculate the conventional entropy. So it involves 2 different steps. When we're saying conventional entropy, again, this is a relative point. So when temperature approaches 0K, we know that conventional entropy equals to 0. So this one is like checked. We know that equals to 0 when your temperature is approaching 0K. The question then becomes, how do we calculate your entropy change at some constant pressure? Because we can talk about the, we can keep our temperature changing, but our pressure is kept constant when we're calculating the conventional entropy. You can fix that pressure at any point, but let's keep the pressure fixed so it's easier for us to calculate it. And in this process, what do we know? Now, again, we have delta S equals to the integral of our dq reversible over T. But we're keeping it at constant pressure. Our dq reversible equals to Qp, which equals to delta H and Cp dt. Right, so this relationship we've seen several times already. Or taking it together, delta S is equal to Cp over T dt. So that is the relationship we will be using in this whole process. Just at different stage, we're using it differently. With me so far? So then we'll use one example, which is water, to see how people calculate the conventional entropy from the bottom up. That means we start from the third law of thermodynamics, saying like when we're having temperature equals to 0K, we have the conventional entropy equals to 0. So we start from there, and then we eventually build it up so that we have the, for example, your conventional entropy of water as a liquid in some random final temperature, maybe room temperature, at 1 atm. All right, so let's see how that's being done every step along the way. So our initial state is your water in solid phase at 0K. So that we know my initial point is S0 equals to 0. What we want is your final conventional entropy for liquid water at some final temperature. And in this process, obviously, we have several different steps taking the way. The first step is bringing your solid water from 0K, gradually increase its temperature reversibly, so it reaches to a point where your temperature is at its melting point. It's not melting yet, but it's solid at its melting point. Second step is now we have the melting taking place at the melting point between solid to liquid. And at the end, we have the temperature rise up from your melting point to its final temperature desired. Pretty straightforward, and you should know how to do it by now, but let's just refresh your memory on these applications and see how things are being done. Number one, so we're warming the solid from 0K to melting point. So our delta SA equals to, well, we'll have integral from 0K to melting point, and we're talking about the Cp over T. For my H2O as a solid, dt. All right, and if we write it out, what effectively do we have is the S naught molar enthalpy, well, this one is molar as well, of my H2O solid minus 0. So that is the S0 we're talking about. That's our original state. And then for our step B, you have delta SB. Well, so that is just a isothermal process. We're just talking about the heat of the melting. So that gives you delta H naught melting of your H2O solid over melting point. Or the other way to put it, this one is your S naught melting at T melting. Forgot the temperature here. Minus in final minus initial. So we have this one to be H2O liquid minus S naught molar T melting H2O solid. Right. So two things, right? So these are just by definition, we're talking about the process of your final state and your initial state. And that's how you calculate that. That's the integral we use to calculate that process. Likewise, we have C, which is warming of your liquid water after it melted. So delta SC equals to, again, an integral between your T melting to your T final equals to C naught PM H2O liquid over T dt, and that's your S naught M T final of your H2O liquid minus, well, this term here. Or what effectively do we want is this term, right? We want the final conventional standard entropy of your liquid water at T final. So we use this whole process to calculate that number by setting up delta S A, B, and C. And in this case, obviously, if we take that delta S as your total, delta S naught M T final of your liquid water, that gives you, oh, I already have it here. That gives you the summation of your delta SA, delta SB, and delta SC. That's the sum of all three steps. I'll just help you by writing out all the integrals here. So the first one is between 0 to T melt CPM of your H2O solid, T dt plus delta H naught melt of H2O solid over T melt, plus that final, which is T melt over to T final, Cp naught of your liquid. You're just writing three integrals together. And in here, some of the terms are easier to solve. So for example, this one, it's pretty straightforward, right? As long as you know the heat of melting, you know how to solve this part. The last part is a little bit more tricky, but I mean, Cp, heat capacity, is something you can measure experimentally. So it is a little bit tricky, but we have some way to calculate it. The first term is a little bit odd because it involves a process where we know that 0K is not experimentally possible. And as a result, your heat capacity is not measurable. When the temperature is very low. 0K to like about 15 Kelvin. So 15 Kelvin is when we say the cutoff point, when you see something called low temperature, normally we set the cut at 15 Kelvin. So below 15 Kelvin, that is the range that we do not have a way to measure the heat capacity experimentally. So we need to take a little bit further look at the process between 0K to 15 Kelvin. So for that, luckily, we have a little bit of help from statistical mechanics. I'm not going to do the derivation with you, but this part, we can just take it as true. And once you learn the statistical mechanics, you can come back and check out whether or not that is how that comes. So we're talking about the molar heat capacity for temperature, for very low temperature. So that low temperature means 0 to 15K. Right. So 0 to 15K. We're saying that is roughly equals to A, which is a constant, times the cube of your temperature. So A is some random constant. And this relationship is derived pure theoretically from statistical mechanics. Now, with this relationship in hand, we can then further derive our first integral into two parts. Right, so this term here, the 0 to T melting of your heat capacity you can further write it as from 0 to 15 Kelvin equals to AT cubed over T dt. N plus a normal one that you can evaluate using the experimental heat capacity data from 15 Kelvin to T melting. That's the C naught T dt. Right, so this one is something you can get from experimental measurement, and this part is being derived using statistical mechanics. And if we focus on the integral here, what do we have? So from 0 to 15 Kelvin, we're talking about AT cubed over T, so this cancel out to be 2 dt. A is a coefficient, we take it out. We're talking about 0 to 15 Kelvin, T squared dt. And we take the integral for that process. We end up having 3 a to the t to a times t to the third between your 0 to 15K. Well, and in this case, your AT to the third, that's roughly your heat capacity. So sometimes people also write this term as C naught PM T low over 3. All right. This one is just simple calculus. And I know it looks weird, but this one is just using simple calculus, and we find this relationship. Or the take-home message is that this entire thing, we now have a way to calculate. Between 0 to 15 Kelvin, we're using the relationship we derived using statistical mechanics. This term, we're using the experimental measured heat capacity. And as a little bit of the extra reading, the change of standard state molar entropy between real and ideal gas is included in your textbook. We're not going over it in detail, but if we ever talk about it, we'll give you a number for this integral that's involved. It's a little bit of extra reading if you're interested. So far what we did is go back to this process, right? We have a way to calculate your conventional standard molar entropy of a molecule or like substance at any temperature. So let's look at an actual application in using these equations to calculate to get some number in there. So this one is your experimental 5.7. So again, if you don't have a copy of the question on your tablet, just take a picture of the problem, and we'll continue working on it. So let's read it. This is one of those longer problems. So for sulfur dioxide, it's giving you the normal melting and boiling point at certain temperature. It gives you the heat of fusion and vaporization, so your delta H fusion, delta H vaporization. It also tells you what is the graph of your heat capacity at 1 atm versus ln K. All right, so one of the things to pay attention to, we're talking about CPM versus ln K in this figure. So this plot is from 15K to 298 Kelvin. So again, we don't know what heat capacity looks like below 15K, so we don't have that number here. It tells you some more information. So at 15.0K, your standard heat capacity equals to 0.83. So that tells you what is your heat capacity low equals to at low temperature. So that means you don't need to calculate that coefficient that's already given. And it also tells you the difference between your ideal gas and real gas as a constant, and asks you to estimate the conventional molar entropy of your gas phase sulfur dioxide. So how do we set up this calculation? So take a picture here and let's do it stepwise, like one step at a time. A few things we want to know before we jump in and solve the problem. So for example, we need a way to solve this integral Cp, the molar heat capacity, over T dt, right? We need a way to evaluate that integral. So by looking at it, the plot gives you the heat capacity versus the logarithm of temperature. So using calculus, we have the logarithm of ln T over dt equals to 1 over T. And as a result here, we can write our dt equals to T d ln T, or if we plug this back in to dt, what we have is the integral of CPM, well, actually I don't need that line anymore, d ln T. So these two terms are equivalent to each other. So if we look back to the figure, well, we're estimating this integral here. We're just looking at the area below the curve where we have y-axis to be the heat capacity, the x-axis to be the ln T. All right, so that's one of the questions is why on some of the thermodynamic pictures, people are plotting it against ln T, or eventually we'll see against 1 over T. What is the reason behind it? It's easier for us to evaluate the integral that way. Okay, so take a picture if you don't have it, and we're ready to get started. First thing first, when we're talking about any thermodynamic problems, let's just write out what is our initial state. So here we're talking about our initial state to always be my temperature approaching 0 Kelvin, and it's in condensed form or solid form. So what do we have? Well, we have the first S equals to 0, S0 equals to 0 for that process. What about our state 2? It is easier to think about the process now between your 0 Kelvin to 15 Kelvin. We have an expression to estimate what is our delta S for the process. So our state 2 is temperature equals to 15 K solid. So for this process, the equation we're using, or the molar entropy of change between 1 to 2, is the one we just derived, which is here, right? So that's the Cp naught T low over straight. And do we have that number? We do. So in this case, we read that at 15 Kelvin, your heat capacity equals to a number. So we have that number here. So that gives you C naught PM low temperature over 3, that is 0.83 Kelvin, calorie per mole per Kelvin over 3. All right, so that's the first step. Then what is the next step? So between state 2 and state 3, we're ready to melt all our solid into liquid. Or, well, before we melt it, we need to raise the temperature to a melting point. So to state 3, we're changing our temperature into melting point. And go back to our melting point is 197.6. And we still have a solid here. And for this process, we have the delta S 2 to 3. That gives you the logarithm, well, the integral of 15K to 197.6K Cp over T dt, where that actually equals to the ln T. And on the top, we have ln 197.6K. And Cp d ln T. All right, so keep in mind, now we're talking about ln T on your integral. And that we can estimate by looking at the area below the curve. So it's roughly a triangle here. The number will change a little bit, but basically we're talking about estimating the difference here using the triangle. So it's 1/2 ln 197.6 over 15 times, well, the height here is about 16, if we look at right. So we're just estimating what that integral is by looking at the area below the curve. All right, so that's our state 3. The next step is the actual melting, or the phase change. So going to state 4. So what do we want? We want the temperature is again at the melting point. And it is now a liquid. Or the delta S of this process equals to delta H melting over T melting. And both of the numbers we have by reading the question, we have the heat of fusion and also we have the melting point. So we can just plug in the numbers there. 1796 Kelvin per mole over 197.6 Kelvin. All right. And what's next? Now we're going back to this figure again, right? We now at the melting point, and then we have melted all my solid SO2 into liquid SO2. The next step is evaluate that integral again using the area below the curve of your liquid section of your heat capacity. Or the way to put it is now we have phase change again into state 5. Now your T5 equals to your vaporization temperature. And that is 263.1 Kelvin. And we're still in liquid phase. And this, again, is evaluating by that area below the curve. So that is between 4 to 5. Well, depending on how you like to evaluate it, that's 1/2 times, well, this one is about 21 and 19. So 21 plus 19 times ln 263.1 over 197.6. And what's next? Now we're at the vaporization temperature. We have a liquid. We want it to vaporize into gas phase. So I'll do the same again to vaporize it into state 6. So your T6 equals to T vaporization. That remains the same. But we have gas phase. And in this case, we are talking about real gas in the reaction. And this process, we have the same kind of equation to use, which is the delta H vaporization over vaporization temperature. And you have numbers to plug in. All right. And the next step is to bring the temperature further up from your vaporization temperature, which is 263.1 Kelvin, into what we want, which is 298 Kelvin. So that's, again, another phase change that you can evaluate using the area below the curve here. We're almost there. I know this process is a little bit tedious. So we have state 7. So T7 equals to T final equals to 298 Kelvin. And we have real gas. Now your delta, the molar entropy change between 6 to 7 is roughly estimated by the area below the curve. So what do we have? That's about 10. And we're talking about 10 of it. We're talking about that rectangular to be 10 times ln final minus initial. Okay, and now we have real gases. And then we have to talk about the ideal gases. Now, between your state 7 to state 8, we're just transferring your gas from real gas into ideal gases. So T7 equals to T final. And we want my gas to be ideal. So this one is just using that number that's provided. So the difference between your real and ideal gases is about 0.07. So it's just a number that's been given. So for this process, we have delta S between 7 to 8. That's final minus initial, so S ideal minus S real. So ideal minus real, that's 0.07. All right. And finally, final. I know I said final, but one last step here is we're having this graph at 1 atm. And remember, we're asked to estimate the standard molar entropy. So that standard molar entropy means my pressure is at 1 bar. So we need to take consideration of that pressure difference between 1 atm and 1 bar. So that means in our state 8, we have pressure equals to 1 atm. And in our final state, we need our T9 equals to T final, and my gas is ideal. I want my pressure to equal to 1 bar. Right, so 1 atm is about 760 torr. I think I made a typo in my annotated note. 1 bar is about 750 torr. This process, we're talking about ideal gases. So entropy change of ideal gases, that's something we covered again in our previous lectures. So refresh your memory on that. Delta S molar of 8 to 9 equals to integral of your R over V dV. And you can do that calculation to get your R ln V9 over V8. And since we're talking about an ideal gas, the pressure and volume is like reversed. So what do we have here? You can plug in the numbers and evaluate that calculation. So the final result is to add everything up. So you have an expression of every step along the way, and the final result of this question is delta SM of 298. You're adding everything up to get a number. You can compare that number with the textbook result. All right. So this one is just a demonstration in how people actually calculate that table of conventional entropy. Normally, you don't have to do that derivation when you're using the thermodynamic table, but I found it very useful to at least show you one time in how people get to that thermodynamic table. Okay, so we have about 5 minutes. So again, this is the thermodynamic table we're talking about. So here, that's the standard enthalpy of formation. That's our conventional standard molar entropy of a specific substance. I don't think I have time to cover free energy, but it's pretty straightforward. We'll go over it on Wednesday. I have a few more minutes left. Let's just quickly talk about the standard entropy of reaction. So again, this one is similar to the standard enthalpy of reaction. Well, we have a general reaction. So in this case, you have like 0 on the left-hand side. On the right-hand side, you have your stoichiometric coefficients, and negative for reactant, positive for product, pretty standard. And our standard entropy change of the reaction, well, that's equals to S naught at some temperature gives you the summation of all your stoichiometric coefficient times the standard molar entropy of that substance at certain temperature. Or one of the questions you might expect to know is use that thermodynamic table to find out the entropy change of the reaction, say ammonia reacting with oxygen to give you nitrogen and water, and find out the overall entropy for this reaction. So we have delta S naught 298 equals to the summation of my coefficient and your conventional molar entropy. So we need NH3, O2, N2, and H2O. And what you do is you go to the table and you find, let's see. We need NH3. Let's find NH3 gas, that's here, and oxygen. Nitrogen. And H2O. It's here. All right. And the problem asks you for the entropy change. So just identify these numbers and plug in the relationship we have. So one of the things just to keep in mind is when you're reading this thermodynamic table, you see that the standard delta H and delta G for these condensed form or your reference point like O2 gas, these are just zero that we discussed before. But note that the conventional entropy at 298 degrees is never zero. It's always have a number there. And we went over that tedious process in how we end up getting those numbers for the conventional entropy. All right, so today we went over a long and tedious derivation in how people actually get these numbers. So some of the questions, once you finish, you can check your results with the numbers here. That might be a good practice if you like. And let's see, we have 2 minutes. I don't want to rush it. So in our next lecture, we'll go over the standard Gibbs energy of reaction. You might already seen it in your discussion worksheet, and if not, we will have something for you next Wednesday. And we will go over 6.1 to 6.3, depending on how long I go in Wednesday class. All right, that's all.